we will go for the last example. I walk you to that. Okay. All right. Just get this on right screen. Okay, so we're here. You made it already to your first 3D dynamic rupture model, and you did a kinematic simulation. Wait, let me try this again. Okay, and the kinematic simulation that we just did of the Northridge earthquake. And now we're getting to one of the more complex dynamic rupture simulations that we can handle with SeisSol, and that's we're trying to understand the rupture dynamics of a very surprising earthquake that happened in 2018. It was a strike slip earthquake, slipping underneath, partially submerged under a small bay, and actually causing a tsunami in that bay, a localized tsunami that was very destructive. And that really changed the way we're looking at the tsunami hazard of strike slip faults. The setup that we prepared for you is, I show you in a minute, but if you already want to look at the notebook, it's in the Sulawesi folder, and then there's a Jupyter notebook there that you can set up. And the simulation will run for quite some time, because this is actually just a quietly smaller setup of the model that we published, so of our actual production run. Okay. Seems like I have this again, just reminding everyone of the website and all these other resources we can look at. And now we are in the last example. So the paper that goes with this is has been published in Pure and Applied Geophysics in 2019. I can link that later. But I took the figures from there. And it's the same geometry that we're using in the example. So this is the hypercenter of the event. It went super shear, which was something that was realized very quickly based on novel seismic array analysis, and also based on geodetic analysis. There were 2 papers in Nature Geoscience showing that this was a super shear event relatively quickly. And there's still ongoing discussion about if super shear contributed to tsunami generation or not. What's important for us now is that we show you how to get an actual complicated fault system with some bends, with 3 segments that are intersecting into these rupture simulations. So this is the map view. You can see there's a northern bend. There's a bend here where the second segment connects to the last one. And we also have variations in the dip angle. So these segments are dipping 65 degrees east, and the last segment is vertically dipping. And to better visualize this 3D structure, here's a couple of more snapshots illustrating the fault system. I want to highlight that accounting for intersecting faults in dynamic rupture models is really challenging, and it's not many codes that allow you to do that. Normally, you either have to have a gap between segments, which will change how these faults interact, because the direct branching is different to rupture jumping, or you have to prescribe like a main fault and then a secondary fault, which doesn't have necessarily the same physics, and that is related to how these rupture boundary conditions are implemented. It's a bit technical, but what's important to understand is that this is something interesting to get in your model. It's also interesting from the meshing point of view to intersect these segments. If they're curved and undulating, that is not necessarily trivial to set up meshes that have this intersections defined in a non-manifold way. So defined in a way that allows us to perform simulations with high quality meshes. This is a snapshot of how your simulation will look like. We have our faults. You see the seismic waves being emitted here, and you can see that we have this MAC cone of the super shear rupture here. So these are S waves being stacked up by the earthquake propagating faster than the S wave speed of the surrounding medium. It goes super shear, similar to an airplane breaking through the wall of sound. This is an earthquake breaking through the wall of S wave speed. It was a very devastating event, and it was a surprise tsunami since it was caused by a strike slip earthquake. And I just want to highlight how many people were affected by that. we're looking at the interesting physics of that earthquake. And we should keep in mind that this was the fact that this caused a tsunami, and we look into maybe how these models can help us understand why, at a huge toll. There's a huge toll related to that. There's more than 500,000 people were affected, and we had 2,100 fatalities. It was also an interesting earthquake in that sense that it was one of the first ones that was, broadly covered and discussed by earthquake scientists on social media. And there's actually a paper published in Geoscience Communications, where this is one of the examples of how Twitter, I guess old Twitter, could be helpful in collecting information and connecting geoscientists after large geohazards to compare data and come up with rapid response, including physics-based modeling. There's a lot of information that we knew 1 day or 5 days after the earthquake. And this is also the kind of data that we need to inform these dynamic rupture models. So for example, fault geometry, which can be mapped from geodetic images, with some first order information about hypercentral depth, and how far slip extended, and these kind of information. So this is all that was needed to build up these dynamic rupture simulations. You would say that this is a sparse data situation. So compared to what I said in the morning, that we are increasingly data rich, in regions like here on the island of Sulawesi, we are not data rich in the sense that we don't have a strong ground motion network sitting on top of the fault, as is run by AFAD for the Eastern Anatolian fault zone. We also don't have a dense network of high-rate GPS stations recording that earthquake. We are data sparse in a sense, but we have regional data. So we had the fault system relatively quickly mapped out from Sentinel-2 and SAR data and regional seismicity. We have information about that can help us constrain the loading and the strength on the fault based on world stress map, for example, and some structural geological inferences that this should be a transtensional regime. And then we can constrain rupture dynamics by asking the model, to not die out prematurely and to be energetic enough to overcome these geometric barriers that the fault is posing. So these are really kind of strong barriers, these bends and fault intersections that require a certain stress drop for the earthquake to overcome dynamically. So this is one of the fault geometry is a first order constraint on rupture dynamics. And we can compare to teleseismics. There was a question before in the chat, so we do that here. We are producing teleseismics and then compare them to the recordings. And another teleseismic inference, moment rate release, so the source time function of that earthquake. So model setup, this is a slide by Thomas, where he basically summarizes again what I had in the morning, but specific for this earthquake, we have our fault geometry mapped out from geological map and from geodesy. We impose a regional stress tensor. So, this is really just our stress tensor, which we are constraining based on the tectonics. And then we can explore different hypotheses, for example, about, the regional tectonic loading. So which direction points an average maximum compressive stress towards that fault system, which would change how much shear stress and how much normal stress is loading that fault system based on variations in that angle. And then we are running our simulation, as you will see. It will start already a super shear rupture. It will overcome this first bend, having strong surface reflections, and it will branch all the way to the last segment. But it is super shear right from the beginning. And we can do some iterations to better fit data, but it's not an inversion, it's forward models. I said that this is especially interesting to look at rupture dynamics to be able to explain the tsunami that was generated. So this is a linked tsunami model, which uses the output that as you will produce at the free surface, how Earth moves up and down close to the source. And we can use this to source a tsunami model. And that is what we did here. I mean, with some additional complexity, also off-fault damage. And we show that the earthquake uplift is enough to explain the tsunami amplitudes that were caused here. to first order. There might be also landsliding sources, but this is really a dynamic effect that we see quite some uplift being produced by a strike slip earthquake breaking through this complicated dipping fault system. It's just a couple of visualizations. You can try to reproduce them, but if you're putting cross sections over, what happens at the surface, we see this step, this uplift, even though it's strike slip motion of up to 1.5 meters. And this is tsunami synthetics. And this is inundation, so run up along the coast compared to observations. Okay, just a short mention, something that we don't cover, but what SeisSol is also able to do now is that we have fully coupled earthquake tsunami modeling all in SeisSol. So this has been something that's been recently implemented by another PhD student, Lukas Krenz, who isn't here, but is enjoying his Friday evening, I think, in Munich. And the idea is to have one model that has the earthquake, the dynamic rupture, the seismic waves, acoustic waves in the ocean, and gravity wave, which is our tsunami. And this is very interesting because normally we're linking, right? We have a tsunami solver, maybe a shallow water equation solver that is using the earthquake displacements as an input. But to really understand what happens during tsunami generation, it is interesting to look, at more complex modeling techniques. So if one of you is interested in tsunami modeling, please ask more on Slack. That is something we did for the supercomputing conference 2 years ago, is that we're running that example that you are looking at, that you will be looking at now, with an additional water layer atop, producing acoustic waves and tsunami waves in that water in the same simulation. And that's an interesting computational problem, because you need much smaller elements to model the acoustic wave propagation. So it makes the simulations more expensive by adding more physics. You can see the earthquake propagating through, you see the seismic waves reverberating, and at some point you will also see the tsunami starting here at a much longer time scale. And then, scaling. This was a very successful scaling on Frontera, where we had almost very high performance. Okay, but going to the notebook now. 1 second, I just have to change my screen. You can ask me questions while I'm firing it up. I show you what I'm doing. You can work along. Okay. All right. So I'm finding my Docker, and I'm starting the ARM one. You can do this also here if you like graphical user interfaces. I'm waiting for my links to pop up. I'm starting Jupyter Lab in my browser. And I'm navigating to the Sulawesi folder, which is here. Double click, open the notebook, which is here, and walk you through. There's another example that we don't have time to go through of the Kaikoa earthquake if you want to play with that later. Okay, again, here's the link to the publication. Linking back to day one, we typically publish all files, all SeisSol input files, including the meshes, to be able to reproduce these simulations. So in principle, you can find any publication of our group, download the input files and rerun it using SeisSol. A couple of introductory material. The first thing that we're covering here is the mesh that we're using. So as I said, in this case, we have not only topography and bathymetry, and we want to account for this bathtub shaped like Palu Bay. We also have these intersecting complicated faults. So this is something that we are not able to do yet with GMesh or with GMSH. So for this, we're using SimModeler. You can click on this. This is Symmetrics is an academic spin-off company, which is fostering to engineers. But for academic use, this is free to use, and this is the software that we're using. And there is actually some very long videos. If you're interested, you can click here and here, where we are showing all of the steps to generate these meshes with SimModeler. There's no voiceover. It's just you can just click, but you can just observe what we're doing. Thomas doing in this case. But it gives you a nice overview, of what is required to build these meshes. So for example, here we're cutting and an upper part of our mesh setup. Let's see if we find something interesting. This is about how these faults that you've seen are being intersected, right? So as you can see, we first intersect them a little bit extruded, and then later on we want to cut some parts. So these are kind of steps that we have to do manually to constrain these models. It's quite similar to constructing a community fault model. It's not so different to what geologists are interested in when they're setting up these fault models that you can just download now. But in this case, we had to do this ourselves. So this is the first video. Now these faults are sticking out, so they have to be cut to not to smoothly intersect with topography. And as you can see, it is quite convenient using that tool. There's another video which is just showing how the meshing works and which parameters we're typically using when we're generating the meshes. It's nice to look at because you can see that we're taking advantage of using unstructured meshes. That means we can zoom in to areas of interest where we need higher resolution. So on the faults, we want to resolve rupture dynamics, we need smaller elements. And in other regions further away, we can use much larger elements. So this is static adaptivity, something that unstructured meshes allow you to do. And it's further saving computational costs compared to having equal resolution everywhere in the domain. You can choose different boundary conditions, so free surface, rupture dynamics, absorbing boundary conditions in this case. That's what you can see here. So there's these two 10-minute videos that walk you through, what we were doing to set up these meshes. Oops. Okay, so this is how the mesh is being generated. In this case, it doesn't take too long, couple of minutes. If we are generating meshes that are larger, it can require a supercomputer itself to produce the meshes. So I'm not sure what our current record is. Maybe Sebastian and Nico can put it on Slack if we 900 million elements maybe or something, but these kind of jobs need they need a supercomputer. We typically run generating these large meshes for testing out Frontera, for example, or running large like Hero One kind of simulations. It's impressive to see that, and what we're learning is super useful. But for studies where we're really interested in real earthquakes, often we don't need this kind of resolution. So these are much smaller simulations. Okay, you can see some weird stuff going on there in the surface, but you see how much we're refining, right? So how much the element sizes are changing. It looks almost plaque close to the surface here. We're really zooming in, using much smaller elements, much larger elements outside of that region. Okay. Again, if you don't want to use ParaView, this PyVista implemented here, which breaks for me, but it's the same kind of animation that just shows you the mesh. Let's see. Okay. Now here's our now familiar SeisSol command. Again, here are your threads. So as I explained before, we have this mixed parallelization. We use MPI and OpenMP, right? So this is why you can specify threads and MPI tasks. And these numbers together, Sebastian answered that question in the Slack. These numbers together should add up to the cores that you have available on your machine. We're using a fully elastic simulation here. And this is our parameter file. We can have a quick look how this looks like. We provide actually two different parameter files. One uses linear slip weakling friction, one rate and state friction, which gives some interesting and quite some interesting differences. Again, this is a YAML file, so something that is should be human friendly, and it has these groups and tags, how we specify all our input. We've seen that before now. Not sure what. If you have any questions about what certain things mean, there is a lot of all of this should be documented online, or yeah, you can ask. I will run it, but I think it might not run on my M1. yeah, so we do have some problems. Sebastian, could we share to your screen? Because it runs for you for that part. Sebastian's not asleep yet.
Yes, no, I'm
By
not
my
asleep.
soothing
I
voice.
just had go back from the Slack to the Zoom. Okay. So here is the model, and I can just run the code. Okay.
Right. So this simulation is, yeah.
I didn't add that I have 4 threads available.
Okay. But this simulation it will run quite a while if it runs for you. You can also download again the sample output if you're interested. And this is also the same model that we will run on Frontera after lunch. And yeah, you get all of these messages. It runs fine for Sebastian. You know, we have this is an open pull request to improve our M1, M2 container. I will post a link later, and once it's resolved, we will be very, very happy. We're working very hard this week to try and get it resolved, but it's still a problem, unfortunately. Okay. Yeah, it also takes some time for you, Sebastian. Seems.
Yes, it does. I mean, I had the experience with that Zoom really interferes with the speed for the TPV13. I think I had it running in 3 minutes maybe yesterday when I prepared everything, and now it took like 10 minutes. So yeah.
Okay.
Maybe, I mean, if you download the reference solutions, you can visualize them inside the container, which is
Let's do that.
kind of bad.
That's a good idea.
You could go ahead and present the reference solution with ParaView.
Mm-hmm.
So I'm giving the share to you again.
Yeah, just firing up PowerView. Second, so should we share the link on Slack where to download the example output? I actually, before I'm just loading it in PowerView again. I actually walk you through the notebook because there's a couple of interesting tasks that we prepared there for you. Let's see, 1 second. Just show my whole desktop. Okay, so if things work and you can, you could just copy that output, you know, into this output folder, and then the notebook will be able to read it. The first thing that's done here is again some visualization, easier maybe with ParaView. Doesn't work yet now, of course, and we can really nicely look then at the so-called free surface output. So if you're loading that, you will have the fields V1, V2, V3 that are velocities. U1, U2, and U3 are displacements, and we can look at the Mach cone that is being emitted by this super shear earthquake. Another interesting aspect is, if you want, and if everything works for you, you could try and change this earthquake to go subshear, like remove the super shear aspects. So there's a hint here how to do that. If you're running the simulation with rate and state friction, you can change the size of the nucleation. So remember, in a simple setup, we had this patch of our nucleation radius where we are overstressing, for example, to start our rupture. And if you're shrinking that from 1.5 kilometers to 700 meters, the same earthquake simulation will be subshear and will stay subshear and will not go super shear. And that is a very interesting comparative data set, because you can look at the wave field, you know, at the free surface, and it will also change how the earthquake is able to jump from segment to segment. So this is the exercise that we have in here. And now I'm still downloading the data set. 1 second. If you have it, Sebastian, could you could also go ahead. I'm still downloading actually.
I don't have it.
Okay, 1 second.
Unfortunately.
Any questions so far? I think it should be finished in a second for me. We're anyway getting close to our Q&A. But I just see a black screen. Okay. So the output is large. Again, this is really almost the same model we published. So it's supposed to be like a real illustrator of how these simulations and data sets look like. Okay. So I have it now. Just loading it. Output Palu example. Okay. Oh, I should share screen. Okay, so I downloaded this, or if you're patient enough, then or your computer's very fast, you already produced this. This is you know, all the output that's generated, and you will see these output files. They're in XDMF format. I said that quickly, but this is a parallel file format, which is very efficient to be written and read in parallel. So this is not only in that sense a binary format, but it's a modern data format that allows us to have every thread or every process write into this file in a very efficient manner, or read that same file in a very efficient manner. And the information, so the data that is actually held by these files, is in these folders. So you have cell data and vertex data. Remember, we have unstructured meshes, so it's not so simple to know which element is the neighbor to the other element. You need quite some information. And then what you download is not the volume output, but we have the fault output and the surface output. So there's 2 XDMF files that you can load into ParaView. For example, the surface reader, the surface output. And this is how it looks like. You know, this is just a cut of our surface. We can nicely see the topography in that region. And now what we are doing, oops, making this a bit bigger. Hope you can still see ParaView. Is that we can load different fields into this when we're plotting this. A second. And we can also at the same time load and the fault output. And then you will have the fault system, as I explained before, which is sitting underneath here. So you can see that this is a complicated system intersecting and also intersecting with the topobathymetry in that area. Okay. I'm not sure I have to go through this again. I would really prefer to have some time for Q&A. So maybe I should stop sharing and we'll have a look at the Slack. Or if you have any questions, maybe you can unmute yourself and just talk. So we have some time for interaction before we go into lunch in about 13 minutes. Let's see what's going on in Slack. Not much. Yeah, this is the link to download. Okay, there's a good question about is there any way to know beforehand or while the simulation is running how much time it's going to take? And Sebastian's answer is spot on. So we typically have very small, test meshes of our simulations where we're trying out, what's the computational cost. We do have of course some experience about rules of thumb based on the amount of elements that your simulation that your mesh is holding. That is some measure of how expensive the simulation will be. And since it's a high order method, you can also choose the order of accuracy by choosing different basis functions, higher order basis functions or lower order basis functions, which is changing resolution within each element independent of the mesh that we're using. So that is also a factor. Computation time, so if you're running a simulation for 30 seconds or you run it for 60 seconds, that is just a linear scaling, right? So you just double a simulation size. If you're interested in higher frequencies, that is not a linear scaling. So that is increasing your cost to another factor. You can also, if you have a large mesh, run it just for a few time steps and you get a good idea of how expensive that simulation will be, because it scales linear with time. So if you just run it for 0.1 seconds, you see how long it will take and you can extrapolate. Raise your hand if you regret buying an M1. Yes. Sorry about that. It cost us a lot. Cost us a lot of sleep this week. But so the one simulation is working on my M1, and that is the Northridge model with attenuation turned on. I would be interested if that works for everyone. Actually, if you would like to go back to that notebook and try, I would be very interested. It would help us debugging. There's a question about, can you recover different phases, including Rayleigh and Love, if the velocity models included in SeisSol? Do your tsunami simulations include T-waves? So yes, of course we can include Rayleigh and Love waves. It's really the full 3D wave field that we're modeling. T-waves, what's important to understand is that our approximation of tsunamis is a linearized boundary condition at the free surface of the water layer, modifying gravity. So the article that Sebastian shared is interesting. That compares this. So I think this is the answer. We're not including T-waves. Okay, my largest mesh for the Palu scenario, 519 million elements. Nico, what was the largest RidgeQuest mesh you ran on Frontera? Was larger, I think.
Yeah, about 620 million elements.
Okay, so yeah, this is the range of the largest models we're running so far. Is there any trick while you run your SeisSol on HPC for larger model and get heavy outputs? Yes. So if you have large, there's a lot of good discussion here. There's handling this big data that we're producing can be a problem. So there's other tricks that you could do. For example, just copying over one time step at a time. Like you can write all the output and then you can store it in the Scratch, but you might not be interested in actually, copying all of that down to your local storage or to your local machine. And in that case, you can just copy certain time steps you're interested in, or using scripts to post-process directly on the supercomputer. But yes, so dealing with these simulations on high-performance computing infrastructure, and Ian will talk about this after lunch. It's basically everything that you normally do with a click, but it's very quick, like copying a file or something like this. If you're running simulations at that scale, all of this requires some thought, like how to copy files, how to write your files, how to read your files. This is all part. This is part of high performance computing. If you're not just computing a single time step to break a record, like if you actually want to run a simulation that produces meaningful output. So input-output questions is very, very important and can be very cumbersome. I think maybe Sebastian can share some stories, but yes, that is it's certainly a good question. I might have missed it, but how hard is it to change the initial stress conditions? Yeah, you can change anything in these parameter files and see what happens. It's not hard. I don't know if that's the answer. You can just change it. Yes, we have the full tensor for anisotropic models. And that's specifically Sebastian's work. So it's good he says he answers, and maybe we can share the paper for that. So it would be really interesting to get some nice applications for this implementation. Okay, I think this is it. Did I miss something? Was there something new? Oh, how did I get it to work with no fridge? It works for them. It doesn't. I get a segfault error for the first simulation, but for the one with viscoelasticity turned on, it runs fine. But I do think this is just somewhat arbitrary. That's what I'm trying to find out. Is this just an instability of, in general, Docker on the M1 and M2s, or is it something that we need to debug in SeisSol? I'm not sure. So that's why I'm asking if you could try that. If you're on an M1 or M2, it would be useful. We're typically running these trainings also completely on high performance computing infrastructure, but we couldn't have pulled this off for that amount of participants that are here now or that are interested. So in that sense, we're providing this SeisSol to go, but yeah, it has limitations. And also keep in mind, if you're now waiting for the simulation to run, this is a code that's meant to run on a cluster, even on a small institute cluster or on a powerful desktop server, but it's not something that you would necessarily run within Docker on your laptop. It's maybe not the optimal application for that. Even though some students that we've trained earlier have produced results with the Docker version of SeisSol for a year or so of their PhD. So. Okay, 5 more minutes. Anything to add? Sebastian, Nico?
No, not really.
Okay.
There's also GPU support for SeisSol.
Yeah.
So if you have a GPU, you can run maybe on your workstation and get better performance than with the Docker. But we only have limited support of architectures, so it's even more complicated. There are more different GPU vendors and GPU architectures, so it's not that straightforward. But yeah, if you have a GPU for some other reason and you want to use SeisSol, you can make use of that GPU.
That's right. And that's interesting to know, porting the code to different architectures is basically a research topic. Yeah, can be a PhD thesis actually to do that properly without losing performance. Okay, then I would say thanks for participating. And we have a lunch break now until 1. And at 1, Ian will take over with some simple introduction of how to log in and how to submit jobs on Frontera. And those of you that have access will run the last example on Frontera, and then you can have a comparison of how much quicker it will go. It's much quicker.